Great, so we're going to start off this week by looking at 4.3. Okay, and as I said, this is going to finish up all the material that we're going to do with rational functions. Right. So we've talked a lot about graphing. Now we're going to look at how do we solve rational equations. And we'll do some with inequalities as well. Okay, when we do the inequalities, I think we might take more of a graphical approach. But when we do the equations, we're definitely going to look at the algebra part. Okay, so just a reminder, remember what a rational equation is. It's just a fraction with a polynomial in the top and in the bottom. Okay, so something like, I'll show you an example. These are all examples of rational expressions. In this case, we have 3 of them. And we'll look at how to solve that a little bit later on. So we're going to start off with a word problem, but the word problem is going to use a formula that you may or may not remember about distance, rate, and time. Okay, so this is the distance equals rate times time formula. Okay, we're going to use that to jump into example 1. So basically what's happening in this problem is Sue is traveling from one place to another, but she's traveling using 2 different modes of transportation. She's going to take a train for part of it, and then a car for the next part. And they tell us a little bit of information about some of the things that would affect her travels, how far she's traveling, the average speed of the train compared to the car, and things like that. So it says that she started off by driving 30 miles to a train station, and then from there got on a train and went the rest of the way. She traveled a total of 120 miles. We don't know the speed of either the train or the car, but we do know that the train was an average of 20 miles per hour faster than the car. That's all we know. The train was an average of 20 miles per hour faster than the car. So what we want to do is find a formula that's going to represent the time it takes to complete the trip. We're obviously going to need a variable in there as well. And we're going to use, and you could do it different ways, but we're going to let x be our variable, and x is going to represent the speed of the car. So let's just kind of see if we can figure out what the equation is going to kind of like abstract what it's going to look like, and then we'll start plugging in numbers and letters into it. So how many modes of transportation is Sue taking in this problem? Yep, Caleb?
2.
Yeah, she's taking 2. All right. So if you wanted to find, well, what are the 2?
The train and the car.
The train and the car. And if you wanted to find the total time it's going to take for the whole trip, how would you do that taking into account the time spent in each mode of transportation? Yeah, John?
So then the time in the car and then the time in the train and then together.
All right, so yeah, let's just kind of set up that big picture idea. So the total time is going to equal time in the car plus time on the train.
Can you use subscripts for this?
Yeah, you could use like T sub C, we could write it, however you want to. Yeah. I always think it's weird. We use in with car, but you wouldn't say on with car. You wouldn't say like the time on the car. But if you say the time she spends on the train, that sounds normal. Yeah? Huh. All right, so we get the time she spends in the car and the time she's on the train. So we have to figure out how to rewrite our formula for time. Right now our formula is written for distance. If you rearrange that formula, how would you get time by itself? Yes?
Time is distance divided by rate.
Yeah, time is going to be distance divided by rate. All right, so now let's put that idea into the formula. So the total time is going to equal the distance in the car divided by the rate in the car. That's time. Distance divided by rate. So the distance in the car divided by the rate in the car plus distance she goes on the train divided by the rate of train. So in both cases, I have distance divided by rate, which gives you time. Any questions on why distance divided by rate gives you time? All right, so now we need to figure out all of these things. Right, and that's going to equal the total time. Okay, let's see if we can scroll back up and look for the distance that she goes in the car. Okay, do we know the distance that the car travels? Yep.
30 miles.
30 miles, so we can just fill that in. Okay, do we know how we're going to represent the speed of the car? Yeah, we're going to represent that as x. Plus the distance that the train travels. What's the distance that the train travels? We weren't given that, but it is something we can figure out pretty quickly here. Leanne?
90 miles.
It's 90, right? The whole trip was 120, but she did 30 of it in the car. So 90 must have been on the train. So 90. And how about the speed of the train? How are we going to represent the speed of the train, Madison?
X plus 20.
Yeah, it's x plus 20. So there is a formula. And we could say that this is t of x, the time as a function of the speed of the car. So if you tell me the speed of the car, I could plug it in, and I could tell you how long the trip is going to take. Okay, and so for example 1, that's all they wanted us to do. Find an algebraic expression for the time. Questions on that formula?
So they don't want us solving this.
Not in example 1. No, not yet. And we have two separate fractions right now. We may want to put those together at one point with a common denominator. Depends what they ask us to do. Okay. Let's go next page. So here's the same formula that we just had. And they want us to find a few things. Okay, the asymptotes, the zeros, the EBM, and a complete graph. Okay. For some of that, it's easier to leave it separate. But for other things like the EBM, we want to look at the highest degree term in the top divided by the highest degree term in the bottom. You need to have one fraction, not two. Okay, so what would my common denominator be here? John?
Would it be
You don't have to do it out. You just tell me it's going to be two things multiplied together.
30 over at that?
No, it's not going to have anything with the 30 in there. Next.
When you multiply the 30 divided by x plus 20.
So we're going to have to multiply both of these fractions by something. It's like if you had something like this, plus 7 ninths. You have to change both of those fractions to get a common denominator. What would your common denominator be here? 72. How'd you get that?
Multiplying it by multiplying both of them by 9 and 8.
Yeah, multiplying each denominator here by the other one. So the common denominator, the easiest way to find it is just multiply the two that you already have. So what would be our common denominator here? But you don't have to FOIL it out or distribute it out. John?
It would just be x times x plus 20.
Yep. So x plus 20, which means, like if you were doing it here, this would get multiplied by 9 over 9. This would get multiplied by 8 over 8. Each fraction gets multiplied by the other denominator. So this gets multiplied by x plus 20 over x plus 20. This gets multiplied by x over x. So on the left, you're going to end up with, let me do the work off to the side so I can put the final answer right here. 30x plus 600. That's what you get in the top when you do it out. Plus 90x. Okay, so I get 120x plus 600 in the top. Okay. So now we can easily see the highest degree term in the top, which will help us when we do the EBM. All right, so let's start with asymptotes. Okay, let's do the vertical. How many vertical asymptotes would there be in this problem? John?
Vertical asymptotes.
Yep, how many?
3. 2.
Okay, what are you looking for? How are you figuring that out?
No, I'm wrong.
Nick?
One medical asymptote,
All right, how do you find vertical asymptotes?
make the top equal to 0.
When you make the top equal to 0, you're finding X-intercepts. So that is something that sometimes we're asked to find, not on this one, but that is something we've done in the past. Sophie?
Isn't the zeros of the denominator?
Zeros of the denominator, yes. So what are the zeros of the denominator here? Sophie?
0, -20.
So x equals 0, x equals -20. I'm not saying that that makes sense in this problem, because remember, x is the speed of the car, so it may not make sense in terms of the word problem, but that's not what they're asking. So we've got the vertical asymptotes. Let's do the horizontals. And for that, we start with the EBM. What's the highest degree term in the top?
120.
What is it?
120.
120x. And what's the highest degree term in the bottom? Yep.
X squared.
X squared, yes. Okay, divide that out. This is the case where the bigger exponent is in the bottom, so you're going to be left with a variable in the bottom. So there's your EBM, which I'm really going to use to find the horizontal asymptote. Equation of a horizontal asymptote always starts out with which letter? Yeah, we've already done the verticals, so y equals. And what do you let x approach in the EBM? To let it approach what?
0.
Infinity. Okay, we let x get as big as possible. End behavior means what's happening at the end of the function. That's very far away from the origin. So at infinity and negative infinity. What happens to the EBM as x approaches infinity? Yep.
It's closer to 0.
Gets closer to 0. Okay, so there's our horizontal. So we've got that. Okay, and let's see, they want the asymptotes, they want the, okay, they do want the zeros. So we are going to set the numerator equal to 0 and solve. Okay, because they want to know the roots. All right, so I didn't see that at first. Okay, so remember, to find roots, you're basically plugging in, you're finding the x-intercept. That's what a root is. The x-intercept is when y equals 0. Okay, it's the only way that a fraction can ever equal 0 is if the top is 0. So 120x plus 600. And what's that going to be? So we bring that over, cross out 0. And what do I get for my root in this case? Yeah?
-5.
Yep, -5. Again, not sure what that means in terms of a word problem with negative speed. Doesn't really mean anything, but that is the root. And EBM we already did, and a complete graph. Okay. So let's start out with a complete graph showing the whole thing. And then let's do a complete graph of just the values that make sense. All right, so we've got vertical intercepts. Let's go all the way down to like -30. All right, so let's type it in first. Okay, I'm going to type in the one where we combined it all, just because it's one fraction instead of two. So 120x plus 600 divided by, and I'm going to FOIL out the bottom because, again, that's even less parentheses I have to put in this problem. So you'd have x squared plus 20x. This is the easiest way for me to type it in. All right, so now let's think. Vertical intercept, we have one at -20, so let's go a little bit past it. Let's try -40. X max, that's the maximum speed. We don't really have a maximum speed. Let's just, try 80. Y min and Y max. Let's just put those -20 to 20. That'll just zoom us out a little bit. And let's see what our graph looks like. So there you can see your vertical asymptote at -20. You can see another vertical asymptote at 0. So this graph is really broken into 3 parts. Now in the word problem, only one of those parts really makes sense. Out of the 3 parts, which one here makes the most sense? All right, so which part of the 3 graphs there is the part that really makes sense in this word problem? Yeah. The positive part, right? The part in quadrant 1. All right, that really represents what's happening in this problem. So let's set that at 0, and let's set the y min at 0. And that shows a pretty good sketch of what's happening here. So what does that mean in this problem? Looking at that graph and thinking about what it represents, you want to explain to me what's happening there? Well, what is that a graph of? That graph represents, in the context of the word problem,
The time.
the time. So what's happening? Yeah?
It's like approaching the maximum time it would take.
What do you mean?
Like the horizontal asymptote, if it's like nearing 3, then like it could take a maximum of 3 hours.
Well, what is our horizontal asymptote? It's not 3. It's 0. So what does that mean? John?
The distance gets shorter over time.
The distance is fixed.
Well,
Distance is always 120 miles.
The slower the rate, the less you go.
Can you say that again?
The slower the rate, the more time it takes.
The slower the rate, the more time it takes. And what about if you said that kind of the opposite way?
rate, the less time it takes.
Yeah, the faster you go, the less time it takes. But it can't ever be instantaneous. Your time to make this trip will never be 0. It will approach 0 depending on your speed. Okay, so the faster the speed gets, the closer and closer the time approaches 0. Okay, so that's what that graph represents. And if you go infinitely slow, it's going to take forever to complete the trip. Because that's why you have a vertical asymptote at 0. So I think we got everything. So now they're going to ask us something specific. This is usually the easy part. It says Sue has 2 hours to complete the trip. Find the speed she must travel by car, algebraically and graphically. All right, let's do graphically first. How do you think I would figure out when that graph hits 2 hours? What would I have to do? Yeah.
Put a line in at 2.
Yeah, we're going to put a line in it, 2. All right, so we got that. And now what would I have to do? Yeah, find the intercept. So this would also depend on having a window that went high enough. To see that, we do have a window that went high enough. So let's calculate the intersect. And we get a speed in the car. That's what this is. All right, so the speed by car is about 46.46 miles per hour. So 46.46 miles per hour. Yeah?
How can we be sure that the y-axis is in hours?
Because the speeds they gave us in the problem, let me double check and see. She traveled. So we know we've got miles. And the distance in the car, the rate of the car. So what we probably should add, just to clarify that here, is let x be the speed of the car in miles per hour. Now we know we're dealing with hours. Yep. Okay, so any question on that? All right. So now what did it say to do? Solve algebraically. Okay. So to solve it algebraically, we're basically going to do the same thing we did graphically. We're going to set this equation. Let's do this one. We're going to set that equal to 2, and we're going to solve it. So let's write down 2 equals. Someone remind me, what did we have in the bottom? Was it x squared plus 120x?
It was x squared plus 20x.
20x, if we FOILed it out. And then in the top, what did we have?
120x plus 600.
120x plus 600. Okay. So, first thing we'd want to do to solve that is we don't want to have a fraction. So what could I multiply both sides by so that I can get rid of that fraction? Yep.
X squared plus 20x.
Yep. Let's multiply both sides by x squared plus 20x. That cancels that. And then on the left, when we do it, x squared plus 20x, that's going to become a distributive property. So 2x squared plus 40x equals a 120x plus 600. Now, what kind of equation is that? Yeah.
I mean, if we just bring everything to one side, it's quadratic.
Yeah, easy. Just a quadratic. So now we'll just bring everything to one side and solve it. We already know we're not going to be able to factor it because we got a pretty messy answer here. Okay? So we're probably going to have to use what to solve it? Quadratic formula. So we're going to have 2x squared. Let's bring the 120 over. What's 40 minus 120? Yep.
Negative 80x.
Negative 80x minus 600. Now, if you wanted to keep the numbers down in the quadratic formula, you can divide everything by 2 to start. X squared minus 40x minus 300. And let's see what we get. So negative b plus or minus square root of, we get b squared, 1600, minus 4ac, all divided by 2a. Minus a minus will become a plus. What's 1600 plus 1200? Oh, Henry's?
How did you get 1,000?
1,000?
Yeah.
1600.
Oh, thank you.
Yep. So what's 1600 plus 1200? Yep. Go ahead.
2800.
2800. So we get 40 plus or minus the square root of 2800 over 2. Let's round that off and see what we get. So let's do 40 plus square root of 2800 divided by 2, and that gives me 46.46 miles per hour. It's exactly the same speed we got doing it as an intercept. Now, technically I do have a second answer. I have 40 minus the square root of 2800. What do you think would happen if I do that? Yep.
Negative answer.
It would come out as a negative answer. Okay, so the negative answer in the context of the word problem, that doesn't make sense. All right, so we're only going to go with the positive answer. So, questions on how we did that algebraically or graphically? Now, we did something here we kind of have to be a little careful about. We multiplied both sides by something that had a variable in it. When you do that, you can introduce extra answers into the problem that aren't there. Okay? So what can end up happening is we get what's called an extraneous solution. Doesn't mean that we did anything wrong. It just means that you multiplied an expression. You multiplied both sides by an expression that had a variable in it. And you could get an extraneous solution. What that means is it's a solution to the new thing that you created by multiplying both sides by a variable, but it would not work in the original problem before you did that. And I think I have a simple example I can show you in a second. Any question on that idea? So this happens anytime you multiply both sides by a variable. So what that means is you need to check your answer. What usually ends up happening with an extraneous answer in these kinds of problems, when you try to plug it back in, it will cause you to divide by 0. And we can't do that. All right. Let's take a look at this equation. Let's say x plus 3 equals 0. What's the answer to that equation?
-3.
-3. Does everybody agree that's the answer? Is there any other answer? No. Now, let's multiply everything there by the same thing, right? You're allowed to do that. Multiply everything here by x. That gives me x squared plus 3x equals 0. Okay. Multiply everything by x. Does -3 still work? Let's check. What's -3 squared? 9. What's 3 times -3? And is 9 minus 9 0?
Yes.
Okay, so -3 still works. But there's another number that works here too. Anybody see the other number you could plug in for x? You could plug in 0 now. 0 squared is 0. 3 times 0 is 0. 0 plus 0 is 0. So 0 works in this new equation. Does 0 work in the original? No. So you created an extra answer in this equation. Even though you multiplied everything by the same thing, it was a variable. Okay? So 0 would be considered an extraneous solution to this problem. All right. And this is the same example. I just picked a different number, just to illustrate the idea of an extraneous solution. So, the way we're generally going to go about solving rational equations is we don't want to have fractions. Okay, we want to get rid of the fractions. That usually means multiplying by a variable. Okay, so we're going to have to check for an extraneous solution. Okay. So the first thing you have to do is find the least common denominator. I had a problem like this, 2/3 plus 5/4 plus 7/6. And I wanted to add those fractions together. Well, actually, let me make it an equation. And let's say we wanted to solve that equation. Well, the easiest way to solve it would be to multiply everything by the LCD. Okay? And that would get rid of all your fractions. So I would do it times 12, times 12, times 12. And then I could reduce. 3 goes in 1 and 4. 4 goes into itself once and into 12, 3. 6 goes in once. The important thing that happened here is all my denominators are 1s now. So I don't have any fractions left. Any questions on that?
Oh, okay. You were saying it goes in 1, and I thought you were saying like, yeah, I get it now.
So now we're going to do the same thing here, except our least common denominator is going to be something with a variable. Okay, it's not just going to be like the number 12. So, anybody see something you could multiply everything by here, and all the fractions would, all the denominators would come out to 1s, just like they did up above. Let's look at that last denominator for a second. Anybody talk to me about that last denominator, the one on the right? Caleb?
Seems like the denominators of the other two are factors of the final denominator.
Yeah, that always will happen to make these problems kind of work out the way I would like them to. But this is really x minus 1, x minus 3. If it wasn't, life would be a lot harder. But that factors is x minus 1, x minus 3. So what could you multiply everything by that would cancel all the denominators out? And we're going to do it in all 3 spots. Annalise?
I was gonna say x plus 1, x plus 3, but that's not right.
No, because that wouldn't cancel with what's already here. Anyone else have another guess what we're going to multiply by? Yep.
The final denominator.
Which is?
X squared minus 4x plus 3.
And when you factor it, what is that?
X minus 1 and x minus 3.
So let's multiply everything by x minus 1, x minus 3. Same thing here, x minus 1, x minus 3, and x minus 1, x minus 3. And let's cross out what cancels first. When you do that in the first fraction, what is going to cancel out? Is there something in the first fraction now that has the same thing in the top and in the bottom? Caleb?
X minus 1.
Yep, the x minus 1 is gone. What about when we do that in the second fraction? What cancels out, Maddie?
X minus 3.
The x minus 3. And what about when we do that in the third fraction? Okay.
Both.
Yeah, the whole denominator cancels out. So now whatever we're left with is a distributive property. So we're going to multiply this times what's left. Very important you do it like that. Okay, in this case it's a plus, so it doesn't mess anything up, but we are multiplying a plus 1 times that. And then the other side is just 2. So let's do that out. So we're going to get 2x squared minus 6x plus 1 times that is going to stay the same. So it's a plus 1 times x and a plus 1 times negative 1. And you just end up with a quadratic. So that's what basically these turn into most of the time. All right, so 2x squared, let's see, minus 5x minus 3 equals 0. What could we try to do and see if it works? Because if we can do this, it's a little faster than the quadratic formula. Yeah?
Synthetic division.
Since it's already a quadratic, there's no reason we have to do synthetic division to bring it down a power. If it was a cubic and we had to solve it, yes, we'd have to use rational root theorem and synthetic division and go through all that stuff. But in this case, it's already a quadratic. So what's the easiest way to solve a quadratic if it works? Yeah? Factor. Let's try to factor it. So we're going to have a 2x and an x. Let's see, we're going to need a minus and a plus. And let's try 3 and 1. So 2x squared minus 6 plus 1 is a minus 5. Perfect. So let's write down the two answers. What would you plug in for x to make the first factor 0? Yeah.
Negative 1/2.
Negative 1/2. And what would you plug in for x to make the second factor 0? Well, let's see. 3. Now, what did I say to make sure you do?
Check your answer.
Check your answers. One of 3 things could happen. These answers could both work. One of them could work and the other one doesn't. Or they both don't work. Right? In that case, we have to cross them both out. Let's check the 3 first, just because I think that's going to be easier. What happens if you plug 3 back into the original problem? Yeah, you'd end up dividing by 0. You can't do 3 in the bottom, in the denominator of the second fraction. So 3 is what we call an extraneous answer. And I might ask you for that on the test. I might set up a problem like this and put 2 boxes and even tell you you're going to get one answer that works and you're going to get one answer that's extraneous. Tell me which answer works and which answer is extraneous. So in this case, it's just a negative half. You can plug that in and check it, but that will work. That's the answer. Okay, questions on that one? All right, let's try this one. So this is pretty much the same thing as the last one, except they've taken the fraction that was on the other side and they moved it over, which you're going to have to do anyway when you do quadratic formula. So they've already started it equal to 0 for you. All right. So anybody see what you would multiply each one of these fractions by to cancel out all the denominators? Yep. X plus 2. So we're going to do an x plus 2, xx plus 2, xx plus 2. Don't ever FOIL that out, because something is always going to cancel first. Michael, what cancels in the first fraction?
X.
So x gone. All right. Julie, what cancels in the second fraction?
X plus 2.
X plus 2, x plus 2. And how about Maddie, what cancels in the third fraction? Both. So now anything that's left is a distributive property. All right, so let's do out the first one. That's going to be x minus 3 times x plus 2. So that's x squared plus 2x minus 3x. Okay, plus 2 minus 3 gives me a minus 1, minus 6. Here, just to, again, be very clear about what you're distributing, that's a positive 3. If that was a negative right there, you'd be distributing that as well. All right. So, plus 3x. And what about the last part? What's that going to be? Just 6. Now, it's already set up and equal to 0, so just combine your like terms and see what you get. That's kind of nice. Plus 6 minus 6. So now that the constant went away, this is going to be a very easy type of factor. It's just going to be pulling out a GCF. So it's x squared plus 2x equals 0. What's the GCF of x squared and 2x? John? X. Let's pull that out. And what are my two values that would make the first factor and the second factor 0? Yep.
It'd be 0 and -2.
-2. Okay. And Madison, what do I have to do with both of those?
You have to plug them into the original equation.
Okay, so let's scroll back up and let's check 0 and -2. Any thoughts on those answers? Yeah.
0 doesn't work because you're dividing by 0.
Okay.
And neither does -2.
And -2 doesn't work either. This is a problem with no solution. All right. So if both answers were extraneous, you cannot solve this problem. It's impossible. If you were to graph it, it would never touch the x-axis. So in this one, we would just write no solution. It doesn't mean I won't ask you for the extraneous answers. The calculator can't give you those. Only the algebra can. Okay? But you can't solve it. Questions on that? Okay, I'm not going to do one of the third case, but the third case is both answers work. Okay, so we did one where one works, one doesn't. And in this one, they both don't. But you might get one where they both do. Okay, so now going back to that first problem we did, it says, what possible rates could Sue travel at to ensure she completes her trip in less than 2.5 hours? So this is kind of leading us into the last thing for the section. What type of problem is this? Compared to me saying, what speed would she travel at to complete the trip in exactly 2.5 hours versus less than 2.5 hours? Yep.
This is an inequality.
This is an inequality. So to complete a trip in a certain amount of time or less, you have a minimum speed you have to travel at, or more, and you will be guaranteed to complete that trip in that amount of time or less. So let's pretty much do what we did before. We already have all the work done. Just change 2 to 2.5. And once it graphs 2.5, what am I going to calculate? Yep.
The intercept and then everything.
Yep. So I'm going to calculate the intersect. And then I want someone else to tell me the answer. So the number I get when I do the intersect is 34.88. So what's the answer to this problem? At what rates does she have to travel to complete the trip in less than 2.5 hours? John?
X is greater than 34.88.
Yes, because it does say strictly less than. It doesn't say less than or equal. So the speed is about 34.88, or is, I should say not about, is greater than. The speed is greater than 34.88 miles per hour. Any question on that? All right. So when we're solving rational inequalities, remember we've talked about graphs that can have hidden behavior. Okay, I will warn you that that is important for the test. Always have to check if something goes off the screen. Okay. Now, if we're solving algebraically, right, and it's a rational inequality, we can set up a Sine Chart. Okay, remember, a Sine Chart is where you figure out where is it positive, where is it negative, kind of thing. And we can only do that with problems that are factorable. The reason we can't use the same method I just taught you with equations on inequalities is because think about what we did. We multiplied both sides by an expression with a variable. Well, when you're solving an inequality, what's the extra thing that can happen that doesn't happen with an equation? One extra step that you always have to think about when you're solving an inequality. Yeah?
If you have to flip the inequality sign,
And when do you have to flip it?
multiplying or dividing by zero.
Right, you multiply or divide by a negative. Well, if you multiply both sides by something with a variable, I have no idea what that variable is. I can't tell you if it's positive or negative, so I wouldn't know whether or not I should be flipping things. That's why you can't use this approach with an inequality. You don't know what you multiply each side by, because it has a variable. Right, so let's see if we can solve this one, and then I think I had one graphing one, and that's it. Graphing is super easy, but let's do the algebra one first. Okay, two things. First thing is, whenever we used a Sine Chart, does anybody remember what we always had it equal to? Or what was always on the other side? Okay.
Infinity? Oh,
No, it was a number. Sine charts only work if it's equal to a certain number, or if a certain number is on the other side. We'll say it that way. Yep.
0?
0, right? Because you're looking, usually you had something like this. And if you're looking where something times something is less than 0, that can either happen if it's a positive times a negative or a negative times a positive. But you can only really figure that out if it's a 0 on this side. Right? So that's what we have to make sure we have. So, how would I get 0 on the right side? What would I have to do? John? I'd have to subtract 1. So I would have 2x squared plus 6x minus 8 over 2x squared plus 5x minus 3. And now you're subtracting 1. I'm going to write it like this. You can't just subtract 1 from the top or the bottom. Because in order to subtract 1 there, what do I need to have? Yep.
A common denominator.
I need a common denominator, so I gotta deal with that. Chances are, once you find a common denominator, it's gonna be very factorable. It's not gonna come out messy. In fact, it has to be factorable. So, this is kind of like having something like this. 7/3 minus 1 over 1. One of your fractions you don't have to change. The other one you need to have a common denominator for. So in this problem, I would just multiply by 3 over 3. Multiply this fraction by that denominator. What do you think I'm going to do in this problem? Yeah.
over 1 by the denominator that was happening.
Yeah. So what I really want to do is I still want to have a 1 right there, but I want to write 1 like this. 2x squared plus 5x minus 3 over 2x squared plus 5x minus 3. Does everyone agree that this fraction is still 1? It's the same thing in the top and the bottom. But now I have a common denominator, so I can combine the like terms in my numerator. So let's put the denominator, 2x squared plus 5x minus 3. Now be very careful here. You're combining like terms, but think of it this way. That negative is distributed to everything. So what we really have is 2x squared minus 2x squared. What's that? 0, that's gone. 6x minus 5x. What's 6x minus 5x? Yeah? Mabel? 1x. And negative 8 minus 3. What's negative 8 minus 3? Leanne?
Negative 5.
Negative 5. Okay, so the top actually came out even easier than the original problem. We don't even have a quadratic anymore. We still do in the bottom. Okay, so now this has to be factorable or it's not going to work. So let's try to factor it. We're going to try 2x and x. Let's try, I think we factored something like this earlier. I don't know, it looks familiar. Let's try a 3 and a 1. Except I feel like we had a negative 5 here, maybe?
Yeah, it was a negative 5 plus 3.
And a plus 3, so it's almost kind of similar. So let's see, we got 2x and x, 1 and 3. Let's try a plus and a minus. Does that work? That's 6x minus 1x is 5x. Perfect. Everything's factored. Okay, question on that? Now, let's just make a Sine chart. Some people don't need that. For me, it kind of helps me to visualize what's happening. And we're going to make a Sine chart for each factor. What's the root of x minus 5? Caleb?
5.
5. What if you plug in numbers smaller than 5? What do you get in x minus 5? Positive or a negative?
Negative.
Negative. What if you plug in numbers bigger than 5? What do you get?
Positive.
Positive. All right, so now I know where that one is positive and negative. Let's check 2x minus 1. What's the root of 2x minus 1? John? Positive 1/2. If you plug in numbers smaller than 1/2, what do you get for 2x minus 1?
Well, nothing to like. No, negative.
Negative. And what if you plug in a number bigger than 1/2? Positive. If you're not sure, just pick a number and try it. Number smaller than 1/2 is 0. Try plugging in 0 here for x and see what you get. All right, and let's do x plus 3. What's my root of x plus 3, Michael?
Minus 3.
Minus 3. If you plug in numbers smaller than minus 3, try negative 10. It's definitely going to give you a negative. Plug in a number bigger than negative 3, that would be like 0. Give you a positive. All right. Now, combine them together on one number line, and we're going to see where we're either negative or positive. In our case, we're really just looking for the negative. We want to know where we're less than 0. All right, so put all those roots down. So we're going to have 4 sections. We're going to have negative 3. We're going to have 1/2. We're going to have 5. We're going to plug them in, one number from each section, one at a time. any number we want. Okay, you can just make something up. But let's think about a number smaller than -3. So if you want a number to think of in your head, think of -5. And let's plug it in. If you plug -5 into this, what kind of answer do you get? Negative or positive? Negative. So we have a negative over. What if you plug -5 into something like this? What do you get?
Negative.
You get another negative. And what if you plug in a number smaller than -3, or what are we doing? Yeah, smaller than -3 into this one. What kind of answer do you get?
Negative.
You get another negative. What's a negative divided by a negative times a negative?
A negative.
That's a negative. Let's do one more section, but does anyone remember what's supposed to happen? Yeah?
Supposed to alternate.
Supposed to alternate. Let's just make sure we get a positive and then we're good. Pick a number between -3 and 1/2.
0.
0 is easy to think of. So let's plug 0 in and see what happens. What if you plug 0 into the top? What do you get?
Negative.
Yep, you get a negative. What if you plug 0 into this one, the 2x minus 1?
Negative.
You're in the negative again. And what if you plug 0 into this one? Where are you?
Positive.
You're in the positives. What's a negative divided by a negative times a positive? That's positive. So now, we know this is going to happen. Go back up. They want to know where you're less than 0. Right here you're less than 0. And right here. That's the first and that's the second. How would you write this interval? Everything below -3. Yep.
Interval notation?
Yes.
It would be, what was it, parentheses, negative infinity, comma 3. Or -3, sorry.
And what here?
And then, parentheses.
Yes, do not put a bracket. That means include it. We can't include it, well, for 2 reasons. 1, it's said to be strictly less than. 2, if you include -3, you're dividing by 0. So 2 reasons why you don't want it. Or, how would we write the other interval where we are negative? Yep.
Parentheses 1/2. 5. Parentheses.
Perfect. Now see it? Okay, so on a problem where you're solving it algebraically, I will always make sure that it is factorable. If you're looking at it and you're thinking it's not factorable, then you might have done something wrong. You did. Okay. All right. So this one would be harder to do algebraically because look at that numerator, right? That's a 4th degree. Usually we're not going to be able to factor a 4th degree polynomial very easily. So we're just going to graph it and calculate intercepts. All right, so let's type that in. And this will be the last one. So we've got x to the 4th minus 3x cubed plus 2x squared plus 2. You do want to make sure you put all of that in parentheses and then put all of this in parentheses just like that. X minus 2. And what am I going to put on y2? Yeah, 15. So what I'm going to be looking for is where the blue graph is above or equal to the red graph. That's what I want to know. So what I should do is check my window. Let's try like -20 to 20. And for y, I definitely would look at negatives as well. Let's do -20 to 20. I'm doing a little more than a standard window because I know I got to go to at least 15 on the y max. So again, where is the graph that curves going to be above 15? So So what I'm going to do is I'm going to set my y max a little higher. I can see a part of that graph that doesn't matter. It's definitely way under 15. I just want to go a little higher and make sure I'm not missing anything. So that part of the graph doesn't matter. It's just going to be that part up there. I want to calculate where I am above that red line. So now that we've zoomed out and we can see there's really nothing more happening, let's go back to just this area. Right about, that's probably close enough. Let's zoom in there. So how am I going to calculate where I am above 15? What do I have to do?
Find the intercept.
Okay, I have to find the intersect. So second calc intersect. Let's do the one on the left. I have no idea where I am. I'm trying to find my point. Okay, so now we got to be careful. I get 2.22. So we can pick anything from somewhere up to or including 2.22, but there is a minimum. What's the minimum? Might help. Let me get the other intersect first, and then let me zoom back out. Alright, so here's the other intersect, which we'll use in a little bit. Just put it up here. I want to stay above, I should have set my y max a little higher. I want to stay above 15, but look at what's happening in the graph. What's happening in this graph that we have to be careful about? Yep.
There's like a section that goes below 15.
Okay, yep, there's a section that goes below. We're going to completely ignore that. So we're going to forget about that bottom section. But something else we have to be careful about here. Lindsay?
There's a vertical asymptote.
There's a vertical asymptote. Where is the vertical asymptote?
2.
2. Good. So you can pick anything between 2 and 2.22, and that'll put you in this section right here. Don't go below 2, then you'll be on the bottom part. All right, so that's that. Or, what do you think the other interval is going to be? From what? Yep.
2.68 to infinity.
Yep, and we can include that because it does say be equal to. So 2.68 to infinity. That's just going to keep going up. Okay, any question on that one? A little bit tricky, but you got to remember that there is an asymptote here, so do not include the 2. You have to put a parenthesis. But you can include the 2.22 and the 2.68 because of that equal to. All right, so let me just fix this a little bit. 1 through... Let's make it easier to write. So it's 1 through 17, just odds, and then 20 to 22, and 24, 28, 31, and 32. And that finishes up rational functions. Okay, so we'll take a look at that tomorrow, and then tomorrow we will finish chapter 4.